Today, I want to introduce formally the axiom of completeness. There are a couple more exercises here under this section 566 that I think might be worth talking to you about just before we actually make the axiom official. People have been submitting this to me, and now I'm stealing it from you. But I think that if you haven't submitted it yet, everybody should have submitted by now at least 3 times. Everybody should have sent me email with attachments. I would say 3 times is par for the course. If you're fewer than 3, like none, is not good. I do want you to know that I have known people to sit quietly in the shadows throughout this course. I don't know the people from a bar of soap. They never send me anything, and they walk into the exams and it's fantastic and I've got no complaints. But more often than not, if you wait for a test to find out whether what you're writing is making sense, you are living dangerously. If you're going to do an act in the circus where you walk a high wire 30 feet above the ground with crocodiles on the one side and flaming knives on the other, it's a good idea to walk that wire a few times only 6 inches from the ground with no crocodiles and no flaming knives until you feel you are stepping safely. Then try it the other way. Okay? Right? So anyway, I feel that I need to say something about this problem. Given that 2 sets A and B are bounded above, explain why the union is bounded above. I'm going to make use of the fact that A is bounded above. Now I'm going to tell you the information given that A is bounded above is a guarantee that there exists an upper bound of A. Isn't that right? Yes. And when something exists, the word is choose. I could begin like this, and I would have no objection if you were to say choose an upper bound, I don't know, P of A. All right? You could. I'm going to put a little bit of bells and whistles on this. And I'm going to remind myself and you as I do this that my ability to make that choice is because of the fact that I'm given that A is bounded above. So the way I'm going to word it is like this. Using the fact that A is bounded above, choose an upper bound P of A. You see? Using the fact that, you never say using the fact that unless you're about to describe an action on your part, not a conclusion. You wouldn't say using the fact that A is bounded above, A has an upper bound. That's it, right? Using the fact, you personally are using the fact that A is bounded above. Using the fact that A is bounded above, I am going to choose an upper bound. You see? I'll tell you something you could say. You could say, because I know that A is bounded above, I know that there exists an upper bound. You could say that. You see? You could even say, and because there exists an upper bound of A, I'm going to choose one. You could say that also. This is a very nice kind of wording. Using the fact that A is bounded above, I, Jonathan Lewin, I'm going to choose an upper bound of A and give it a name, P. And using the fact that, who's downloaded my fragments? few of you. If you put my fragments in, you can get a quick using the fact that by holding control and typing UTFT makes using the fact that. Just thought I'd mention. Save you a bit of writing. Anyway, there are zillions of things. I don't know my fragments, but my fingers know them. Anyway, using the fact that B is bounded above, choose an upper bound. Well, of course, you can give any name you like, but if I call one of them P, how about the other one Q? It's easy on the eyes, right? Of B. Now, I need an upper bound for A union B, isn't that right? What should I do?
You do P plus Q.
Good idea, but not great. It doesn't work. Because if one or other is negative, so adding is dangerous. You could have taken absolute P plus absolute Q, but it's getting messy. There's something much nicer. Define, what should we call it? Rumpelstiltskin, what? W, to be the larger, right? Of the two numbers P and Q. Okay? Now I'm changing color because I'm not claiming to finish. Please finish. What must you do? You must now explain to me why W is an upper bound of A union B. What is your job to prove that W is an upper bound of A union B? You got to prove that for every X in A union B, something happens, and to prove for every, you say, suppose that X belongs to A union B. X belongs to A union B. There are two cases. Either X belongs to A, that's one case, or X belongs to B, that's the other case. Deal with them one at a time. Write it, send it to me. Okay? Thought I would just give you a leg up on this one. Send it off. I'm not talking one more time about the BMW question. You should be sick of it by now. Given that alpha, and let me tell you, I'm going to go through the entire book and remove all the symbols alpha. It's driving you crazy and it's driving me crazy. It looks too much like an A, and it's driving everybody crazy. I'll replace them by U's or W's or something. Anyway, there's still a surviving alpha here. And listen, will you all please, as a compulsive sort of thing, will you always please check for upgrade for your book over and over again. Always take a look and see if there's an upgrade. Bring yourself up to the latest version. Okay? Everybody. Now, we are given that a certain number alpha is sup A. And we are given that X is less than alpha. What conclusion or conclusions can you draw about X? What can you guarantee about a number X, given that alpha is the supremum, the least upper bound, the supremum of A, and that X is less than alpha? What can you conclude? Who's telling me that X is in A? All the hands. Let me see. All the hands. I've got Nicole. You're on your own, right? I've got two people. I'll tell you something. Members of A have to be less than or equal to sup A. Isn't that right? That does not tell you that all numbers less than sup A have to belong to the set. They may or may not belong. Isn't that right? Especially because A might be very broken. Doesn't have to be an interval. See? So folks, just because a number is less than the supremum does not guarantee that the number belongs to the set. It might or might not. I'll tell you something. A number greater than the supremum definitely won't belong because the supremum is an upper bound of the set. But numbers below might belong. So if you can't guarantee that it belongs, What can you guarantee? Maybe nothing. Yes, my lady. All right? I'm neglecting you, right?
X cannot be an upper bound.
What do you think? Right? Who's saying that? X can't be an upper bound of A, right? Make you finish your sentence, right? Strict Lewin, right? Yes, alpha, or super A, whatever you want to call it, is the least upper bound. It's a BMW argument. That's why it appears right here with the BMW question. If you're less than the least, you're not one of them. If you sell more BMWs than anyone in the Southeast, you live somewhere else. You see? It's a BMW argument. That's why it appears as part B of a question where part A was the BMW question. Okay? Who drives a BMW here? None of us can afford one. Actually, quite honestly, I don't know. What do I know about cars? Nothing. I'm not doing part C. Part C is boring once you've done B. I wish I hadn't put it in. Okay, now we're going to talk about the axiom of completeness. What?
Stand on your head and talk about B.
Maybe. Yes, I don't know about standing on my head. What is it? Your old Father William, the young man, said, and the hair on your head is now white, and yet you incessantly stand on your head. Do you feel at your age this is right? Who knows that poem from Alice in Wonderland? In my youth, said the sage, when I stood on my head, I feared it might injure the brain. But now that I'm perfectly sure I have none, why I do it again and again. It was Lewis Carroll's parody of a much earlier, very puritanical poem from the Victorian era. He was mocking that earlier poem. Anyway, the axiom of completeness. You and I have already agreed among ourselves that if a set doesn't have any upper bound at all, there can't be a least one. Thank you so much. If a set doesn't have any upper bound, there can't be a least one. There are no birds to fly, right? More Alice, see? If a set is empty, it's got too many upper bounds. All numbers are upper bounds of the empty set. There can't be a least one because there's no least number. You understand?
Too many clouds in the sky.
So the fact is that in order for a set to have a least upper bound, you need to be sure that there are upper bounds, and you need to be sure that the set is non-empty. And it turns out that's all you need. That's all you need. Here it is. Whenever a set is both bounded above and non-empty, the set has a least upper bound. Please understand that this does not even suggest that the least upper bound has to belong to the set. The least upper bound of a set may or may not belong. Haven't we seen examples like you take an interval running up to its right endpoint, and the right endpoint's not in an open interval, and the supremum, the least upper bound, is that right endpoint doesn't belong. You could have made it belong or not belong, you see? And we've also been playing together with the fact that when the least upper bound of a set happens to belong, then it's the biggest member. Yes? Some people have been writing stuff and sending stuff to me about this very fact. And if you haven't, you are playing with a little bit of fire, but you might be managing very well. But I have a slight anxiety here. Okay. Now, whenever a set is both bounded above and non-empty, the set has a least upper bound. Now, if you stand on your head, this thing is going to say whenever a set is both bounded B lower non-empty, the set has a greatest lower bound. Why don't I so put here? And whenever a set is both bounded below and non-empty, the set has a greatest lower bound. This would be a full statement of the axiom, but watch what I'm going to do. I'm dumping that and I'm putting my period there. What happened to it? I'm not putting that in. It's true, but I'm not putting it into the statement of the axiom. Because it turns out that if you know that whenever a set is both bounded above and non-empty, the set has a supremum, a least upper bound, it will then automatically be true that whenever a set is non-empty and bounded below, it has a greatest lower bound. So I don't want to make both statements. I'll make one as the statement of the axiom of completeness, and the other statement I will state as a theorem. We will say that this now follows logically from the other part of the axiom, and that will give us both. You see? That's the way we're going to do it. Then we've dug a little bit deeper. So I'd like to mention to you that the real number system that we are assuming has been placed in our hands for this kind of level of mathematics is a system with a plus and a times and a 0 and a 1 and a less than and the supremum axiom. That's really what we have assumed. And one day, in some more advanced course, we might say, well, how do you know there is such a thing? Define a number. Tell me what the number 1 means. Tell me what plus means. Tell me what 2 means. Theorem, 1 plus 1 equals 2.
Doesn't that take like a whole book to prove?
Mm-hmm. It's in my foundations course. I'm waiting for somebody to take it. I taught a few people last year. And so anyway, we'll see. It's possible to actually construct that from the Zermelo-Fraenkel axioms. Right now, we're supposing that this is in our pocket. It's handed to us. And the axiom of completeness says that whenever a set is both bounded above and non-empty, the set has a least upper bound. Now we're going to prove a theorem. Get out of there. We assume that a given set A is non-empty and bounded be what? Below, and it is our job to prove that A has a greatest lower bound. That among all the, listen, how do you know there are any lower bounds at all? How do you know there are any lower bounds of the set A?
Bounded below.
The set is bounded below. That means there exist lower bounds. And what I'm actually claiming is that among all the lower bounds, one of them is biggest. That's what I'm claiming. So let's get going. I'm going to start with a definition. I'm introducing a new symbol. We define B to be the set of all lower bounds, can't spell lower, bounds of A. I'm defining B to be the set of all lower bounds of A. You understand? I'd like to mention that we know that the set B is non-empty. How do we know? It's given that A is bounded below. What does it mean, A is bounded below? It's given that there exists some lower bounds. What numbers qualify for membership in this exclusive little club here? What do you have to do before you can join that club? You have to be a lower bound of A. Are there any lower bounds of A? There are. So therefore B is non-empty. I want to tell you that our job is to explain why this set B has a largest member. That's what our job is. Look at what I said. I want to explain, to prove, that means to explain. Prove and explain are the same thing. I want to prove that A has a greatest lower bound. I want to prove that among all the lower bounds of A, there is a biggest one. You understand? All right, so I'm just announcing what I haven't started yet. I haven't started writing anything yet. I'm just kind of asking myself, what is my job here? Now, I'm going to change color, and I'm going to tell you a little mini facts. Yeah, lemma if you like. I want to start by explaining that every member of A has to be an upper bound of B. I want to explain this. It will help with understanding the main thing. I'll go back to yellow when I'm finished this. Tell me, folks, how do you prove a statement that says for every? You write suppose. That's the mantra. To prove for every, say suppose. To use the fact that something exists, say choose. If you know exactly what you mean by something, you can say define, okay? And when do you give an example? To prove that something exists. Okay. I want to prove that every member of A has to be an upper bound of B. So how do you begin such a proof? Suppose that X is a member of A. Isn't that the way you got to prove? If you want to prove that every member of A eats chocolate, suppose that X belongs to A. Now I'm going to another color. I need to explain why every member of B has to be less than or equal to X. You understand, I'm not just writing the proof here. I'm engaging in a little bit of chat with you and teaching. I'm thinking aloud. I'm asking myself, what must I do to prove that this X I introduced with the word suppose? I used the word suppose to introduce a challenger or arbitrary member of A. And I need to explain why this thing is a what? Is an upper bound of B. Well, what does that mean? Ask yourself what it means. You've got to know the definition. If you don't know the definition, you're dead. Nothing to do with how good or bad you are at math. If you don't know what the word means, you can't work with it. You know, if I say, what does it mean for a number to be an upper bound of a set, you've got to be able to say immediately, perfectly. Full sentence, grammatical. Without hesitation. Otherwise, how are you going to write about it? I need to explain why this X is an upper bound of B. I want to show you that every member of A is an upper bound of B. Suppose that X is an A. So ask myself, what does that mean? I need to explain why.
Every member of B is...
I want to prove that every member of B has to be less than or equal to this X. That's what it means. So how do we start? I'm going back to this color. How do you prove that every member of B does something? Yeah?
You're going to use two cases. One works less than one works equal.
I'm not ready for the cases. I need to open it up. I want to prove that every member of B does something. What am I writing? Suppose, yes. Suppose that, what letter should we use? A little b perhaps? Belongs to B, right? Sure. Okay. Now, I don't know why we need cases. I can make it easier. I can say the fact that little b, you remind me what big B is? Who gets to be in big B? The numbers that are lower bounds of A. The fact that little b is a lower bound of A and that this X belongs to A guarantees that B is less than or equal to X. Haven't we done? You understand? I said to you, I need to explain why every member of big B has to be less than or equal to X. Suppose that little b belongs to B. Well, now I'm telling you why it's less than or equal to X. I'm telling you why. The fact that B is a lower bound of A and X belongs to A lower bound of A can't be more than a member. You understand? There you are. So, going back to the yellow. We have seen, I'm going to announce in the yellow, we have seen that every member of A is an upper bound of B. That's what I did here. I explained, you see? I'm just kind of rolling it around my tongue a little bit to show off that I've got this piece of information. You see? Now I want to tell you the set A is non-empty. Is it not? How do you know? It's given. Right?
So
and every member of A is an upper bound of B. Isn't that right? I'm going to tell you, therefore, B has some upper bounds. If I tell you there is at least one person in the next room, everybody in the next room loves you.
There's at least one person.
Then there's at least one person who loves you. The mere knowledge that everybody in the next room loves you
doesn't guarantee
is cold comfort. There may be nobody there, you see. So I've got good news and bad news. They all love you. The bad news is there's nobody there. See?
Every uniform marches knows.
Yeah. So look here. The set A is non-empty, and every member of A is an upper bound of B. Therefore, B has some upper bound. Somebody loves it, right? I'm going to repeat myself. The set B is non-empty. Why was that? I can't remember. I've forgotten. Why was B non-empty? B, what was the definition of B? Remind me. B was the set of all lower bounds of A. And there are some lower bounds of A.
B was defined to be bounded.
A was given to be bounded below. See? So B is non-empty. The set B is non-empty and bounded above. Isn't that right? B is non-empty and bounded above, yes?
So, by the
Therefore, by the axiom of completeness, tells us that B has a least upper bound. Okay? All right. You understand least upper bound is a unique thing? I'm going to write define. Define, what should we call it? What letter haven't I used yet?
Y,
I don't like Y.
J,
That looks too much like an integer.
little
Not if there's a big A.
a, V,
I'll use I'm willing to use a V. Define V to be the supremum, least upper bound of B. Okay? Now I'm going to just pause for a second and I'm going to put my cards on the table. Please remember, go away. Please remember that our objective here is to explain why B has a largest member. Isn't that what we announced? Right? Well, I'm going to tell you that for this purpose, we are going to show that soup B, I believe that was called V or something,
yeah,
belongs to B. That's what it takes for a set to have a largest member. The set is non-empty and bounded above, so it's got a supremum. To show that the set has got something better than just a supremum, our biggest member. You see, not every set's going to have a biggest member. Even if it's non-empty and bounded above, it doesn't have to have a biggest member. We've seen this. You go to the open interval from 1 to 7. It doesn't have a biggest member. Isn't that right? It's got a supremum. So we want to show that B has a biggest member. Well, we know it's got a supremum. It's got a least upper bound. We're going to explain that the least upper bound belongs. When the least upper bound of a set belongs to the set, then
at least upper bound.
then that least upper bound is going to be the biggest member of the set. That's something that we've been talking about. That's something that I wish you had been sending me a lot of mail. Some have. A bunch of you have been sending emails with this very kind of stuff. Others are waiting. I don't know what you're waiting for. You're waiting for me to scream at you. The one thing I'm going to nag you about is that. The other thing is to go on Marketplace. I'm going to read off the registration on Marketplace a week from now, and I'm going there once only. I had an ongoing song and dance last term going into that Marketplace, and I finally got sick and tired of it, and I made a promise to myself that this term I wasn't going to do that. So you better go there and fix it before I go there, because I'm not going there again. If you need my help, if you need me to pay for you, you phone me and tell me that. Anyway, God, it's only $7.80, but if you need me to pay, I'll do it. Now, please remember that our objective is to explain why B has the largest member. I need to explain why soup B belongs to B. I'm sorry, I'm not finished yet. I need to explain. I'm going to ask you one more time. Who gets to belong to this exclusive little club here? What is the criterion to get a membership card to join that little club? Who gets to belong here? You belong to B when you are a what? We need to explain why soup B is a lower bound of A. You understand? Okay, well, I'm almost done. You see, I'm not just writing the proof here for you. I'm talking to you. I'm tearing this whole thing to pieces. By the time you finish and you write it, you're going to write a much shorter proof than this. I'm actually giving you all the thoughts that lead me to do things. I need to explain why sup B is a lower bound of A. Yes? I need to explain. I'm going to ask myself what lower bound means. I need to explain why the inequality sup B, let's try that again, sup B less than or equal to x holds for every x in A. Isn't that the statement that sup B is a lower bound of A? Yes? That's my job, to explain why this inequality holds for every x in A. How do you go? I'm going back to the yellow. The color here is as much, is as important as everything else. It's the words, no. It's the color in which I'm writing it, you see. That's why it's so important that you look at my notes. Don't try and study from your notes. Besides, I see what students write, takes 6 months off my life. So anyway, how do you prove that something happens for every x in A? To prove for every, say, suppose that x belongs to A. Now, why should sup B? I called it V or something and then completely forgot I had done that. Very well. I don't think I need that V. Well, since sup B is the least, I'll shout it, least upper bound of B, and x is an upper bound. Haven't we already explained that every member of A is an upper bound of B? Okay. X is an upper bound of B, and sup B is the least upper bound of B. We can see at once that sup B is less than or equal to x. Do you understand? What I said, we need to explain, we got it. See? Look here. If I say, somebody, I'll pick on somebody here and say, is in this room. And I say, somebody else is the youngest person in the room. What can you deduce? The somebody else got to be not older than the first person. Isn't that right? I know this number, sup B, is the least upper bound of A, and this x that I've introduced here is some unknown upper bound of A. The least one has to be less than or equal to any other one. Isn't that right? There we go. So, is this the only way to write the proof? Hell no. I'm sure there are lots and lots of ways. If I were to write this proof again now, I'd probably write it totally differently. And if you can remember what you wrote, and you're trying to go through all the words to try and get the same words, if you're doing that, you haven't learned any math. If you say, okay, this is what Lewin gives. If we write this, then you write this, then you write this, then you write this, you get the proof. If you're doing that, you haven't learned anything. What you've got to do is you've got to be in a position where you can't remember which way we did it, but it comes out of your heart. So there it is. It's quite a difficult proof, actually. I've spent quite a lot of time on it. And I'll tell you what you have to do to explain, to make this proof understood for yourself, to explain it to yourself. You have to find a ready victim and explain it to that person to your satisfaction that you did a great job of teaching it. And when you have done that, the other person will not understand a thing, but you will. The person doing the talking gets to understand it. That's the name of the game with math. Yes, sir?
Two questions. Do we need to say that suppose that x is in set A twice, even though we can find it above?
This was for a totally different purpose, and that's all gone. It was in order to achieve a certain task, and the letter X is gone and lost at this point. This suppose X belongs to A was done here with the purpose of explaining something. We ended that explanation, and in fact, the changing of color here was an indication that we're really doing a new proof. So if it bothers you, we must change letter. But you see that suppose X belongs to A over there was for some other purpose of which I've forgotten what it was. I think we wanted to say that every member of A was something, eats bananas or something, you see. And once you've explained that, that's over and the letter X is gone, you see. You could never, for example, say, I know that X does something. I'll say, what X are you talking about? Oh, the X over there. I'll say, wait a minute. That was from some proof that has been completed, you see. So that answers that question. It was a good question. What's your other one?
Okay. Every time we use sub B, do we need to define it as the least upper bound, or can it just be assumed as long as we
Sorry, every time.
Because like you said, since sub B is the least upper bound.
Oh, I see, super. Well, this symbol, this is the symbol for the supremum of a set, and we've proved that B does have a supremum, and the supremum is always written this way.
So do we have to say it's the least upper bound, or can we just say since sub B exists?
Where?
Right there.
Didn't I say it exists or somewhere?
Yeah, why do you have to say since it is
Here,
separate?
the set B is non-empty and bounded above, therefore, therefore, the axiom of completeness tells us that B is the least upper bound. I can now write sup B as often as I like.
He's just saying,
I've already said that B has the least upper bound.
he's just saying, why do you have to write since B is the least upper bound of B and X is the upper bound?
Oh, I'm just emphasizing, you see, I've shouted the word least. Sup B is the least upper bound of B, and this other Charlie is an upper bound, therefore sup B is less than or equal to the other Charlie. That was the point.
Just emphasis.
Okay, well, folks, let's see if we can do some of these exercises. The first one is a bit of a paper tiger. You know what a paper tiger is? It looks very fierce, and turns out it can't harm you because it's only made of paper. In an earlier exercise, we saw that if you have a set A that is non-empty and bounded, and you have a little a is a member and is not the largest member, you understand the set has no largest member. In an earlier life, last week or whenever, we proved that this set A and this slightly smaller set have the same set of upper bounds. Remember? The numbers that are upper bounds of this set are precisely the same numbers as the numbers that are upper bounds of that set. Was an earlier exercise. And therefore the least upper bound of A and the least upper bound of A slash singleton A are the same because the sets have the same set of upper bound. And so the least one is the least one. You know, if you were to say, I will give the name Rumpelstiltskin to the set of upper bounds of A, well, Rumpelstiltskin is also the set of upper bounds of the other set. And the least member of that set, Rumpelstiltskin, happens to be the least upper bound of A, and it's also the least upper bound of the other set. So this is a sort of, it is an anticlimax. It really follows the other exercise. Let's look at number 2. Exercise 2, we're given two sets, A and B, of numbers. And you're given that this one is non-empty and this one is bounded above. And this one, you know what that symbol stands for? Subset. We can read A is a subset of B. You can also read A is included. That's the word, included, okay? Included means subset of, okay? Don't confuse with belongs to, which means member of, okay? It's not here. Included means subset of. You will never hear me use the word contained in, because I'm never sure which way that's going to be understood. If a word is ambiguous, I chuck it out completely. That is why I forbid you to ever use the word let in mathematical writing.
What makes it worse is that the shortcut for the element of symbol, belongs to symbol, is in.
In. Yeah. IN. Control. IN. Okay. Now, you are given that A is a subset of B. What is this statement? Every member of A has got to be a what? A member of B. That's what's given. Explain why sup A and sup B must exist and why sup A must be less than or equal to sup B. And I'm going to talk to you. I'm stealing the problem from you because I feel that to a large extent your experience standing on my shoulders rather than trying things totally on your own in isolation will help you learn the material. Very often students send something to me and I'm very frustrated. The student is battling and I can tell this student has not gone through the lecture and is trying to do some problem from the exercises in isolation from the course. And I write back and I say, look, this stuff is a mess. I can tell that you've sent this prematurely. You should first have studied and rewritten the stuff we did in class a few times until you are on top of that. Then you should try this unseen proof. You understand? Don't send something prematurely. All right, so anyway, I want to tell you something. We are given that A is non-empty. Yes? Mm-hmm. And that every member of A must belong to B. Isn't that given? Let me tell you something. B is non-empty. There are members of A, and all members of A belong to B. Therefore, there are numbers that belong to B, right? B is non-empty. And B is bounded above. Okay? Give me a moment. I want to explain something. We are given that B is bounded above. Do you understand? Please make sure you can see that every upper bound of B has to be an upper bound of A. I'll answer questions in just a minute. There are upper bounds of B. Yes? There are upper bounds of B, and every upper bound of B has to be an upper bound of A. Why? Why? So how would, let's take a, suppose that I want to prove that every upper bound of B, suppose that W is an upper bound of B. How do you know that W is an upper bound of A? You're going to write this. Suppose that X belongs to A. Well, this X must belong to B, and therefore it's less than or equal to W. You understand? I shouldn't have said that. I wanted you to do it. See? So I'm coming back to the yellow. Therefore, A is also bounded above. Are you with me? so far, we know that both A and B are non-empty and both A and B are bounded above. I've gone as far as explaining why these both exist. You can now use the axiom of completeness to guarantee that sup A and sup B make sense because both sets are non-empty and both sets are bounded above. Now finish. Okay, this is the last part. Okay, let me see what sort of feedback I get. Explain now why sup A has to be less than or equal to sup B. I'm going to leave that to see what sort of stuff you send me. Kim, you had something to ask me.
So if A is in B.
I don't know what you mean.
Right, if the set A is included in B.
Well, you don't have to say if, it's given information. We can say we know that A is included in B, so we don't have to say if then. Okay?
This is where I said, I'm sorry. I can see it, but I don't know how to
But the important thing is that because A is a subset of B and A is known to be non-empty, B has members. Anyway, take a look at that. I want to do number 3. I'm looking to see. Yeah, we can do it. Number 3. Is it always true that if you have a set that the inf of the set is less than or equal to sup of the set? Is it always true?
No, sometimes.
Well, what if inf the set and sup of the set don't even make sense, right? What if they don't make sense? Yes? Well, what are we given? We're given that A is non-empty and bounded, both above and below, right? So therefore, inf A and sup A do make sense, all right? So why do you think inf A can't be more than sup A? I'm actually going to open this to the floor. Wait. Who's been quiet up to now? Why can't inf A, the greatest lower bound, be more than sup A? Tell me, my lady.
Suppose X is in the set A.
I don't think you want to prove something for every X in A. I think you're using the fact that A is non-empty. I think you should have said,
Okay, so we
choose a member of A, period. Yes, now talk to me.
the definition of intimum A is it is the least,
Greatest
the greatest lower bound
of A.
of
Yeah.
A.
Yeah.
So, and then we compare it to the definition of sup of A.
Yeah, speak more loudly if you can.
So that definition is the least upper bound. So
Yes.
it's got to be greater than the lower bound.
Greater than all. You know, you started off pretty well, but you kind of lost me. You started off by saying, choose a member X of A. You're so close. He's almost there. Are you really, you know, I was about to say it, but now I'm seeing some life from Kerry here. Talk to me.
Okay, so we'll go with choose X, a member of A.
Yes, we've chosen X in A.
By definition, we know that inf A is less than or equal to X.
Because inf A is a lower bound. The fact that it's the greatest is not even important. Inf A is a lower bound of A. Inf A is less than or equal to X. And talk to me, lady.
And by definition, we know that X is less than or equal than sup A?
Yeah, well, you know, this by definition, because sup A is an upper bound of A, X is less than or equal to sup A. You know, by definition, I'm not so sure which definition, you see, but because sup A is known to be an upper bound, I don't even care that it's the least upper bound. Any old upper bound would have been just as good, you see. So X is less than or equal to sup A for that reason. Well, inf A is less than or equal to this particular number, X, and this particular number is less than or equal to sup A. You were there, but you just were being a bad teacher, you see. So, folks, that's that one. Right. And I think I'll make a few quick statements about, I'm going to make a few quick statements about number 5. The reason, by the way, I put stars here because I'm having trouble bringing the little logo, you know, that little question mark thing. It's a hell of a job for me to put it into the lecture notes. I can't just paste from the book, because otherwise in your copy and from your computers, the thing is going to come without the picture. It's a bit of a pain, so I got lazy. I just put a star. The stars here indicate that these are the exercises when you go to the text that have the help. Okay. Anyway, because that one has help, I think I'm going to talk about this one very briefly. I'm not doing it all. You given A and B are non-empty, and you're told something rather strange. For every X in A and every Y in B, X must be less than Y. I'm going to ask you a question. Is X in A? Answer me. Is X in A? The answer is I have no idea. I have no idea what the symbol X stands for. When you say that for every member X of A and every member Y of B something happens, that doesn't give you a particular number called X. If I tell you every person in this room likes ice cream, have I singled out anybody and said something?
No.
I haven't. I've made a general for every statement, you see? Don't come and say, well, X does this, Y does that, right? You can't do that. Yes, my lady.
So, because we see this, do we say suppose X is a L?
I don't know. We haven't started a proof yet. We haven't started I'm just reading the information. That's all I've done. I don't know. Actually, what does it say? Prove that sup A is less than or equal to inf B. That's what we have to prove. Right? Whether we're going to say suppose, we have to ask ourselves what it is we want to prove, right? Prove that sup A is less than or equal to inf B. Actually, I want to tell you something. If you can prove that sup A is a lower bound of B, it'll be less than or equal to the greatest lower bound of B. There's my suggestion. Okay? Alternatively, another way to approach this, if you can prove that inf B is an upper bound of A, it'll be at least as much as the least upper bound of A. Now let me see whether I can't get some life into more of you. I should be absolutely inundated with mail. You should be sending me stuff. I get some people who send me stuff and then they apologize. Sorry, I'm sending you so much. I say, please, it's the people who aren't sending who should be saying sorry. Okay? So that's the story, folks. Go do some study. Okay? I'm no longer recording.